3, then you can tamper with the 2 other ballots and change the ballot as such. It's also an extremely user-unfriendly approach if you get to more complex elections, and if you force people to mark every row to start with, I think that's nothing that really will be appealing to voters. It might enhance auditability. So if you are the voting authority, and if nobody complains, you have a good chance that everything went well and you had no errors in your process. But it doesn't enhance transparency because it requires trust in the checker mechanism rather than in the counting. The integrity of the two ballots that you don't copy is at risk. And why don't you trust the counting in the first place? Before I move on to the 2 other approaches, I'm going to introduce some fundamental concepts, which many of you might be aware of anyway, or better than I am. Mixnets is one introduced by David Shorm in the early 80s. It's used for many other things than just voting, for email, anonymization, and things like that. In elections, if you want to use mixnets, you basically you have keys which permute your initial votes. So if I have a candidate B here, then and a candidate A here, then I mix that in the next step with the permutation key, and I can use have many of these keys, and these keys can be controlled by different people, and that's really the key of it, so that nobody really has the entire knowledge to understand how is this information on the left-hand side be transformed in the information on the right-hand side. So I can count something through a mixnet without revealing the anonymity of the vote. Rivas and others in 2002 have suggested to use these mixnets in e-voting in 2002, and they've introduced something like what they call randomized partial checking. And what you do is you look at a pair of keys or pair of servers or whatever you want to call it, and if you go to the middle column here, to the information in the middle column, you throw a dice for each of these bits or information pieces, and you either then check and open the left-hand side of the connection or the right-hand side. So if there's some, and then you compare the values on both sides, and if you have the same in both boxes, then nobody tampered with. And so if somebody changes something, you have a 50% chance to detect it, because you either have to change it here, or you have to change it here to tamper with the outcome. So for every vote flip, you have a 50% chance to find that in the audit. So to get away with n flip votes, you have a probability of 2 to the minus nth, and that's quite, with a relatively low n, this is already a relatively low chance. So it maintains the secret of the vote despite of an audit. Another concept is commitments, and there's some math below it, and I don't want to go into too much detail, but the math you use is basically that this formula, g to the ith modulo p with any integer I, and with a prime p, creates a permutation of your values. So if I is between, if g is 3 and p is 7, and I is between 0 and 5, then the values for 3 to the ith is this, and and if you do the modulo 7, then you basically get a permutation of your initial numbers. So it creates a pseudo-random permutation of your initial sequence. And for large primes, it's very difficult to solve for I with a given C and a given G. Now, you can use that to commit to a secret. Commit in terms of that you can't change it after you've revealed some information. So if you have two large primes, P and Q Q divides P minus 1, and you have a private key A, and you have a public key H, which is G to the 8th modulus P, and you can commit to a secret X by choosing a random R and publish a C, which is calculated like that, and if you reveal then R and X, the receiver can verify that you actually didn't change your X after you committed to the secret. That's not very intuitive, and I'm not expecting anybody here who hasn't dealt with that before to at first glance understand what this is about, but it gives you a feeling on what complex or how complex and how mathematical the tools are that are used in cryptography. And if you introduce cryptography into elections, then basically if somebody wants to understand that his vote is secret and to understand that he can check his the integrity of the election, he needs to go to that math, and that's nothing that you explain your grandma on a beer tap. Now, David Shorm introduced PunchScan in 2006, and how does that work? It basically consists of two superimposed sheets, so a blue one at the bottom and a white one at the top, and you have 4 candidates here, and each candidate has a random number next to it. And these random numbers appear in 3 holes from the underneath layer. And if you look carefully, this random order here is different than this random order here. So, and the ballot sheet has a serial number again, and when you vote, you mark your candidate. In this case, candidate A, you mark it at the top and the bottom sheet. And then you separate the sheets and put one in the ballot box and take one home. And none of the two allows you to prove how you voted. So if you look at the top one, because this order here of the numbers was random, it doesn't give you any information what you voted, and same at the bottom. You voted for 4, what that is, you don't know with the other half of the sheet. And obviously you can't count that without knowing how that hangs together, but you can hide that information in a mixed net, and you can commit to the corresponding value through to randomized partial checking. And then in the end, all receipts are published on a bulletin board, and you can go to that bulletin board after the election and check whether your vote is there as you casted it. Now, the initial version of PunchScan was not protected against coercion, and that's because if you have a 2-candidate race here with 2 candidates, and you force somebody, or you give an award to somebody to either bring the top layer with a 1 assigned to candidate A and the left hole marked, or you bring the bottom layer where the 1 appears, where the 1 appears in the left and is marked, then you have in 3 of the 4 cases you're actually able to fulfill that requirement, and in two of the cases you've actually voted for candidate B, and only in one you have voted for candidate A. So you can incentivize people to vote in a certain way. Now, if you have more than one candidate, that attack weakens, but it doesn't go away. And it's because, well, the reason for that is that you first mark and then you make the choice whether to keep the top or the bottom letter. If you have to make that commitment before you see the ballot sheet, that attack goes away, and that's basically then punch scan 2. But even though this attack is not is resolved, it indicates one issue that is very important with all these cryptographic methods, and that is the sequence of events is very important. So who commits first to the next action is essential for the secrecy, for the integrity of the approach. Scantegrity is a successor of PunchScan of the same group of authors. It's a similar concept, but not on one sheet, but all on one sheet. There's random codes next to the candidate names, and then the ballot paper is scanned, and the codes related to the chosen candidates are published. And there's a second version of that where you only uncover the random codes of the chosen candidates, but not of the others. And that introduces an easier complaint validation process, because you don't know the codes of the candidates you didn't choose. But what's interesting is that the same authors who published the first approach, PunchScan, then felt the need to introduce subsequent versions or subsequent approaches. So something that was meant as a serious proposal in the first place then wasn't good enough later. Bingo voting is by a German team in 2007, and that's a little different approach. You have a preparation phase where for each voter you prepare a random number for every candidate, and they call that dummy votes. So basically you have a pool of random numbers here for candidate A and for candidate B, and they all get committed to with a method, with one of these commitment methods I briefly talked about before, and then they're shuffled and published on a bulletin board. Now, in the voting phase, the voter selects a candidate, in this case, candidate A, and there's a trusted random number generator who pulls a new random number, and that's where the name bingo voting is coming from. Bingo, like they're suggesting a mechanical random device to make sure it's really random or trusted random. Now, when they did a proof of concept for a University of Karlsruhe election, they didn't use a bingo cage, they used an electronic device. So the trusted random number generator creates a random number, and you receive a receipt which has this trusted random number next to the candidate you chose, and random number from the pool next to the other candidates. So you basically, by voting for candidate A, you are reducing the number of remaining random numbers for each candidate. And the receipt you take home, and the receipt is also published on the bulletin board, and you go home and you check that your vote has been, or that your receipt appears on the bulletin board. Now, how do you determine the results? you just count the remaining dummy votes in the initial pool, because now you've used 3 votes for candidate B, C, and D. They have 1 vote less than the others. In the post-voting phase, you publish the results, You publish all receipts. You list all the unused dummy votes and corresponding commitments, and you prove that everybody